Whew, okay, made it barely. We, few of us did a tour of the TTU steam plant today, and it's pretty interesting. Get over there and see what they're doing. I emailed this out the other day, and I would not have started compressed air, but I forgot about this article, and so I'm going to cover this a little bit, and then we'll jump back over to the compressed air presentation. You know, we need to be looking at a pump test pretty soon. Let me come back over here and put a calendar up and see. I haven't really set a date. You guys need to be working that homework, and I had a question whether I want it turned in. I think you probably should email me a solution file on that. You know, I'll probably give everybody 100 that does a reasonable. I mean, I've sent you the solution, so I mean, come on, how hard can it be? But just so that I know you've touched it a little bit and looked at it. There's some pretty good questions. They're not terribly well defined. Oh, Don Cassida wrote that as a qualifying exam in order to just take the PSAT class. So he wanted to put people through that much torture before he would let them take his qualification class. But I think it's pretty good. As far as a test is concerned, you know, I don't know, I'll take some feedback. I would think maybe the 19th might be a pretty good day for the pump test. It gives you a little bit of time to look at it. I mean, we could do the 17th. Does anybody have any strong preferences? Well, the longer you wait, the more you forget. But I don't really care. I would say 17 or 19 is when we need to take that pump test.
Hey, I like the 19th. Give me more time to study 19th. For it.
Put it off later. You know, you might get run over by a car on the 18th. You know, and you wouldn't want to spend your last. You wouldn't want to spend your you know, haven't taken a test you didn't have to take. Right? Okay. All right. We'll set the pump test on the 19th. It'll be iLearn. It'll be a bunch of questions. I think I pretty well got it input. I haven't looked at it for a little while, so I'll look at it and give you some more feedback. Yes?
I think someone wrote a message in the chat on Zoom. It just popped up when you were on the phone.
So I got a little chat going on here, huh? Well, let's see here. Chat. 19th. Okay, that does it. David, you were the determining factor. So the 19th it is. Okay.
Speaking about this, as far as the final class, when will that fall? Does it look fall on the week of the first?
It's whenever the final exam is listed. There's an exam schedule published. You just have to. It's whenever it is, and the exam will just be on compressed air. We don't go back, and I don't go back and test over the other modules. I think that would be just too much material for you. Okay, so that's good. So let's. This is a very good paper. So this guy, I mean, it's in a journal. I mean, a magazine, Pumps and Systems, but this guy knows what he's doing. And, you know, because if you go out and work in the world and any place around pumps, you're going to see people just blindly applying the affinity laws. And you should know, at least after you get finished studying for the exam, you'll remember that the affinity laws are used to adjust a pump curve. The system operates at the intersection of the system curve and the pump curve. So that's where the rubber meets the road. But you see people violating that all over the place. And so that's why this guy did this study and has put this paper together. So I don't know. I haven't looked at this in a while. The pump affinity rules describe how a pump's performance will change with the speed or the impeller diameter. But you have to incorporate the system curve to get a correct result. Okay, so he's got 3 piping systems here, figure 1. Each system consists of a supply and product tank, a variable speed pump, valves, and interconnecting pipelines. Working fluid is standard water, density 62.37 pounds per cubic foot. Each system has the same pump selected to meet an operating point of 1,000 GPM at 98 feet of total head at 1735 RPM. But each has a different amount of static and dynamic head, achieved by varying the total pipe length and product tank elevations. So he's gonna monkey with the elevation of the tanks to adjust the static head on this and see the impact. I think we've kind of done this, but I think it's good to revisit. So system 1, system 2, system 3. So system 1 is all frictional. That's all dynamic head. No static, all friction. And so you achieve that by having these 2 tanks that are exactly the same elevation and the same level, and no gas, and the same gas overpressure, which probably means they're just open to atmosphere. Okay, so we see supply tank 1, level 20 feet, elevation 0. Product tank 1, level 20 feet, elevation 0. So VFD 1, 1,000 GPM, total developed head, total head, TDH, some people call it, 98.56, 1735 RPM. So that's with a VFD probably on 60 hertz. And the supply pressure is 3.271 PSIG, and the discharge pressure is 35.94. And get my calculator, I did. And so just for the heck of it, if you take 45.94 minus 3.271, you get 42.699. If you multiply that by 2.31, well, you get 98.56. So see, that's the total head. It's just pressure. That tells you the pipe diameters are the same, and there's no loss. There's no K's between the gauges and the pump. You see, so it's all, that whole pressure is made up of just those 2, the suction and discharge, and just converting that from PSIG differential to feet of head. Okay. It's interesting it's good to punch this stuff up every once in a while. When you start matching numbers, you go, oh, okay, I see what he's doing. Okay. So then on system 2, the supply tank 2, it's 0 feet of elevation, and we have a level of 20 feet. And the product tank now is, the level's 20 feet, but it's 25 feet up in the air. Okay, so we've got 25 feet of static head on this system. Okay, and but the pump is still the pump is still operating at the same point. And then for system 3, and so that represents, of the head produced by the pump in system 2, it's 25% static, roughly, because what our static head is 25 divided by what the total head is 90, almost 99. So that's roughly 25%, which means the rest of it has to be frictional head. And then in the third case, we've got this tank 75 feet in the air, and the elevations are both 20 feet. So we say that this is 75% static and 25% dynamic head, still producing the same total head for the system. Okay, and remember, he's changing some of the pipe sizes in order achieved by varying the total pipe length and product elevation. So there's some piping length changes. Okay, so we know the Darcy for the straight pipe, etc. We know the Darcy-Weisbach equation, F L over D, V squared over 2G, where this is the velocity head. Or you can do a translation on it, F L Q over D to the Q squared over D to the fifth. I'm not really familiar with that one. I usually just work with this one. We have an advertisement that was in the magazine. Okay. Okay, so let me make this a little smaller. Okay, so when we plot it up, I mean, we've seen this kind of thing before. So you got system 1, system 2, system 3, from 0 friction to not much friction and a lot of static in between those systems. So I think everybody should be good with looking at those curves. Also, okay, system static head affects pump speed and variable speed applications. So these are the affinity laws, and we know we use those to simply adjust the pump curve for different operating speeds. And then wherever they cross, if you slow that pump curve, it's going to fall down through here. And these three systems are going to operate at the intersection of that system curve and that pump curve at different speeds. Okay, so using the affinity rules to reduce the flow rate by 50%, this just shows how you do it. Remember, this is the affinity law. So, well, this would tell you, he says, okay, he wants to cut the flow rate in half. And so if you want to take this point and translate it to the 50% flow from 1,000, then you can do the math like this. So then the RPM would be half of that, and the head then would be 24.64, okay? So then, let's see, it's been a little while since I've looked at this. Okay, so now we're going to show the three systems again. And let's see, so what are we doing here? So flow 500 GPM. So we've got a pressure of 18.59. I guess that may be here, and I'm not seeing, oh yeah, and on this side, we've got 7.226. So calculated suction and discharge pressures give a head of 26. Okay, for this system, basically he's saying, okay, for these systems at 50% flow, what would they require? Well, at 50% flow, one of them is going to require here, the second one's here, and the third one is going to require clear up here. So number 2 is going to require almost 45 feet of head, and number 3 is going to require almost 81 feet of head. Okay, and so you can't just blindly cut this speed in half and expect that that's where all three of these systems are going to operate. If I cut this speed in half, this curve is going to shrink down through here, and it's going to go through roughly, well, this point shrunk down to, what was it, about 25 feet of head. So the all frictional system is going to work pretty much. So that curve is going to be way down here. With 50% speed, this system would produce flow back here someplace, and this system wouldn't produce any flow. That's what he's kind of trying to get to. Okay. Calculating total head required. So, okay, and this is showing he's just showing the calculation. This is 2.31 times the differential pressure, so 26 feet. Okay, system pump speeds calculated to match the head requirements of each system. Okay, so this guy, let's see, pump VFD speed, okay. So this one can operate at 895 and be on the curve. So let's see up here, when we cut this speed in half, say this is 867, it's pretty close. 867 got us about 24.6 feet. Well, it's got to be a little faster because I need 26.25 feet. So we had to speed it up a little bit for system one, but it's pretty close. So the all frictional follows the speed relation pretty well. For this system, and at this operating point, we're 56% static and 44% dynamic. We need a speed of 1140. So 1140 RPM, we put the pump curve through this point. That's what we're doing. He's calculated the RPM required to put the pump curve through this point because he wants 50% flow. And so this one's going to be up in the 80s. So it's not going to get slowed down very much at all. 1530 RPM in order to get us the 81.31 feet of head that system requires at 500 GPM. Okay. So there you go. There's his analysis. And so what you do is you plot these system curves, you get in Excel, and you figure out what flow you want, and then you can do it trial and error. You just put in the different RPMs, and this curve jumps. And it gets shorter too. He drew it all the way out here. That point will shrink down like this, so that part's not quite right, but the rest of it is. So at 1530 RPM, this pump curve shrinks into this one, and it goes through my desired operating point. At 1140 RPM, it shrinks more, and it goes through this desired operating point. And at 895, it shrinks to this point, which is what I want for that system. And notice the affinity law, if I just translate the points to 50% speed, I get this curve. And so that curve really doesn't go through any one of the 3 points. And that's the point of the article, is you can't just use the affinity laws. And so then the other thing you have to, if you want to calculate the operating cost, you have to determine, well, what's the pump efficiency going to be at the reduced speed? And so you can see if you have for different RPMs, different efficiencies. So you're over here at like 89% efficiency, but with this static system, when I slow this thing down, I'm going to be just a little over 70, so maybe 73, 74% efficient. When I do it on this second curve, I'm going to be better. I'm going to be about 83%. And on the all frictional curve, it's pretty much the same. I'm going to be 88, 89%. So that has to be taken into consideration. So let's see, operating costs vary with different amounts of static head. So fixed speed pump with throttle valve. So if we did it, let's see, for system one, variable speed, annual savings. Okay, so if instead of using speed control, I just throttled the flow on the all frictional system, it would cost, well, in this case, it's going to be the same, 17,200. With variable speed operation, it would drop it to 11,400. Savings of $5,800 for, say, putting the variable speed, if you had to add a variable speed drive. If you had the second system with 75% dynamic head, you would only save $4,700 because of the way the pump curve falls along that system curve. And then for the final case, which was static dominated, we would only save $2,000. So conclusion is, you got to pay attention to your static head if you're looking at a pumping project to reduce energy by, say, going to speed control on a pump. Okay, well, that was a little rough. I hadn't looked at that article in a while, but I think we got through most of it there. So, questions? Y'all kind of get the gist of it. It's a pretty clearly written article, so I will probably draw some test questions out of this because I really like this article. Yeah. Okay, let me do one other thing here. So I sent, let me see, what do I want to show you? So I sent Oak Ridge kind of a nasty gram the other day because I started to record a video of me using the measure tool to do a pump analysis. And I don't know if you remember that really inefficient system at the end of the pump slides, the one that was 6,100 GPM, and it was pumping so efficiently, just the pump itself. And then there was a recirculation line right downstream on the pump discharge, and then there was a throttling valve. So I was going to redo that analysis in measure. And I'll tell you, you just about can't do it. Let me see, where did I, pumping system, so slides for Tina. So Tina's a lady that is one of the programmers. She's a mechanical engineer. And so I just sent her, so I just sent her these slides, you know, and it's got, you know, we went through all this in great detail. It's got the pump head calculations, it's got the PSAT analysis, all this sort of thing. Okay. So you start trying to do this in measure, and it's virtually impossible. I'd say it's totally impossible. But let's see, I think I probably have. Yeah, this is it right here. Okay, so system setup. So this is measure. And it tries to do the right thing. But, so, you know, just units, pumping fluid. So I put in the type of pump, I put in the RPM, direct drive, water, you know, all this is good. put in the motor information, 60 hertz, 350, energy efficient, all that. It didn't really like the, you know, we had a list at 80 full load amps. It doesn't really like that value, but it'll take it. So that's not an issue. Then you get your field data. And so this is what, now it does make a comment that it doesn't think that you can get 6,100 gallons out of this type of pump. I don't know. I didn't make this example. If this is one that was in the field, then obviously that's incorrect, but that's neither here nor there. So there, we calculated pump head as we had before. So that's fine. It's about 193 feet. I think it was 193.5 or something before, but that's okay. Measured current and voltage. So these numbers are okay. And you go, okay. Well, if you recall, the first thing that we wanted to do is we wanted to change the flow rate to 3160 because the rest of the flow was recirculating back to the suction tank. So I said, okay, well, let me do my assessment here. And so let me see. Scenario, required flow, 3160. Well, and so if you do, so this is really not install VFD. This was just to reduce the flow rate, right? 3160. And here's the analysis. And this shows a savings by just reducing the flow rate of $130,000. Now there's no savings. This is incorrect. And if you look at the PSAT result, let me just make this one bigger. There you go. So this is the initial analysis, $171,300, agrees perfectly. Copy it over here, change the flow, and this is the result. Well, it's still $171,300, right? Because I didn't change the motor amps, and I didn't change the voltage. And look, my pump efficiency is 45.4% because I'm still using the same power, and now I'm only really pushing 3160 GPM that I'm actually using. The rest of it's just going around in a circle. Okay. Well, look what Measure does. Measure forces me to keep the pump efficiency the same. I can't change it. The only input, I could change the pump head, but I don't want to change the pump head. Okay. I could change the pump head. I don't want to do that. I could adjust the operational data. That's the cost of electricity and the number of hours per year. I don't want to do that. I can install a more efficient motor, but I don't want to do that. It's already got an energy efficient motor. I got nowhere to go there. Install a more efficient pump. Well, let me see. I didn't try this. I guess I could put, can I put 45 on this? 45. But see, that means I'm going to have to go calculate. I'm going to have to go do hand calculations to know what efficiency to put in here. Or I guess I can run it in PSAT, 45.4, and then I can go to Measure. If I'm going to run it in PSAT, what do I need Measure for? That's ridiculous. These people have spent God knows how long. More efficient drive, okay, I can put a belt drive on it. I can install a VFD. Okay, so if I click the install VFD, it does give me an efficiency box. But again, I have to go calculate it. What's the point? Now, you know, if you're running the project exactly the way they want you to run the project, then this will probably work. But the way this example is set up, you basically can't do this analysis. You can't repeat this analysis without doing hand calculations in Measure. So anyway, I sent them a nasty gram and they haven't replied. I send them nasty grams all the time about their software. But anyway, so my undying recommendation for you is download PSAT while you can, if you ever think you're going to need to do some pumping analysis, because this thing is flipping pretty good. It puts it all right there in front of you. All right, I'll get off my soapbox now. Quit pounding DOE. Somebody needs to. Okay, let's see. Compressed air. Okay. Is this where we finished? I'm sorry? I can't hear you. Speak up. 39. 39. Thank you. Thank you, dear. You got to get rid of that nice voice around me. You can't be. It takes people a while to learn they can't be nice with me. Okay. Oh, yes. Compressed air generation. I remember now. Okay. Well, great topic. So, common compressor types. Positive displacement. What's that mean, positive displacement? It takes a volume of air and it squeezes it by reducing the volume, like a piston cylinder, like a rotary screw. Okay, those are our two primary types. And then dynamic, that means that's like a fan. That's a really high-speed, high-pressure fan. Suckers turn 40 to 60,000 RPM. Can you imagine building a rotor that's going to spin at 60,000 RPM? What if you nicked a little piece of material off of that? It'd probably tear itself apart. And those machines, they all have vibration sensors on them. But these centrifugal machines really have vibration sensors on them because they're afraid if something goes wrong at those speeds, this thing will shake itself to pieces in a hurry. So anyway, but that's the dynamic. It's has more characteristics of a fan than positive displacement. So there's a big difference in some of the operating characteristics that we'll see if we're talking about positive displacement or centrifugal. Centrifugal tend to be very large machines. They're very good machines. They're expensive machines. And the old Cooper Cameron and some of those things, you find them out there 30, 35 years old, still home. Because maybe they knew how to build a compressor. Ingersoll Rand has purchased that, and we'll see how they do with ownership. But anyway, and Ingersoll Rand makes one. All the big guys make the big centrifugals. A small centrifugal is probably 400 horsepower. A big centrifugal, I've seen them 5,000 horsepower. 5,000 horsepower motor is a pretty good sized motor. I'd say the average is probably 1,000 to 1,500. Was in a General Motors. Is it General Motors? General Motors or Ford? I think it was General Motors. Up in Michigan, I participated in a big assessment up there. They were running 35,000 horsepower of air compressors. 35,000 horsepower. That's a bunch of compressors. Yeah. So anyway, the centrifugal, they tend to be the workhorse of large industry. And if you get them and you operate them within the correct parameters, they are probably the most efficient that you can have. But they're not very flexible in terms of their unloading, as we'll see. So there can be huge waste associated with them. Reciprocating, we don't see too many of those anymore. In the old days, I would say 40, 50 years ago, they were very common. Large ones, big pistons, 15, 14, 16-inch diameter. Boom, boom, boom. You could feel the pulse, you could feel the concrete shake when you would walk up to one of these things. The big double-acting recips. When they went to install one, they would have to cut slab and dig out the rock, and they would have to pour 4 to 6 foot of concrete and set the anchor bolts in to hold them down. I swear, you walk up these things, I mean, you get like from here to halfway down the hall, and in your feet, you feel the pulses, you feel the boom, 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 boom. They're not super loud, but because that piston is not just flying back and forth, boom, 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 something like that, whatever, maybe a pulse and a half a second. And then the screws, the rotary screw compressor, that's pretty much the workhorse these days for small, medium-sized compressed air systems. You see more rotary screws than you do anything else these days. That's a rotary screw compressor in the picture. We'll talk more about it. Okay, we have some equations. What are engineers without equations, right? So this would be the input power, the rate of doing work, or probably kW, or whatever units. I'm not sure what units come out of this thing. K, specific heat ratio for air, 1.4. K minus 1 over K. V dot I, that's the inlet airflow, volumetric airflow, cubic feet per minute at the inlet of the machine. So that's at inlet conditions, or it could be at standard. You could take it at standard conditions or inlet conditions. But, 14.5, 14.7, 14 to 14.7 psi A, and whatever temperature. You could use a standard temperature, or you could use a site-specific temperature. Inlet absolute pressure. What are you going to take? A lot of people, I'd say the standard is probably 14.5 because there's an inlet air filter. And so that air, if it's 14.7 in the surroundings, you draw that air across that filter, you get a little bit of a pressure loss. So the actual compressor sees a little bit less than whatever the atmospheric is because of the inlet pressure drop. And of course, if the filter gets too dirty and you don't change it, well, then that inlet drop can get larger and your inlet pressure gets lower, and that makes your compressor have to do more work to provide the same exit pressure. So a dirty inlet filter is not something that you want to run. And then isentropic efficiency of the compressor. Okay. We can also do it in terms of mass flow rate, even though that's just using the ideal gas law to convert the volume flow and the pressure. But I don't see many people actually doing mass flows through these machines, but I mean, it's possible. This is out there. I've not really used this very much. It's a slide that a friend of mine put together. Been some modeling to try to adjust this, to put this gamma coefficient in, depending on the type of compressor. If you had a single stage reciprocating, it would be 1. If you had a 2-stage reciprocating, it would be 2. If get a single stage oil flooded screw. We'll talk more about that, be 1.25. I don't know. The times I've used this, I pretty much just use it like that. So I don't have much experience with this equation. I'm not sure how good those gammas are. Let me say this. Let's say I was looking at this, and let's say I go into a plant and they're running the compressed air pressure at 125 PSIG. I mean, generally speaking, that's pretty high. You know, most plants can get by at 90, 95. You know, it's pretty standard. You see 100, maybe 105 in the compressor room. So you see 125 and you go, hey man, you really need 125? What's going on here? Oh no, that's just where they like to set it. Well, okay, so why don't we drop this 15? You know, think you could run 105? Well, we try, see what happens. So you're going to do the calculation. So see, what you can do is you have two different, you can apply this equation twice. You can apply it to the initial, and that would be the initial power. And then you can apply it to the modified, and that would be the modified power. And then you can ratio those two equations. And that will tell you the percent that you're going to use. So maybe that ratio comes out 0.9. We go, that says I'm going to save 10%. Okay? And if you do that ratio, if you assume the isentropic efficiency is about constant, it drops out because it cancels. Well, that's nice because then you don't have to run around looking for an isentropic efficiency for this particular compressor. And also, the K-1 drops out. If you assume the volume flow rate is roughly the same, or if you think the volume flow rate is going to change, you could put that in. And the inlet pressure is not going to change. So say really just about everything drops out besides the bracket term. So you've got P exit 125 plus, that's got to be PSIA because this is an ideal gas type relation. You know, so we have to put absolute pressures and temperatures in this stuff. So PE in the first case is 125 plus, say, 14.5, whatever you're taking as the atmospheric pressure, divided by the inlet. Let's say you're figuring 14.5, and that's PSIA. So you take that ratio to the K-1 over K-1, and then you do it again at 105 for PE, and the rest of it is the same, and then you ratio those, and that'll tell you your percent savings. So that's a nice little trick. Now, this works for, and I should say this up here, this works for positive displacement compressors. I would not use this on a centrifugal. I would use this on positive displacement. Because what happens, well, one of the complications on the centrifugal is it's like a fan. And if I reduce the discharge pressure on it, I get more airflow. The power doesn't necessarily go down much, but I get more airflow. The question is, when I get that additional airflow, am I going to use it productively? Because when we get into the control modes on the centrifugal, one of the control modes is blow off, where you actually take compressed air and blow it through the roof because you're making more than your system needs. And so if I'm in blow off and I reduce this pressure, I get a little more air and I blow it through the roof, how much do I save? Nothing. So, you know, you just have to be real careful with centrifugals. And we'll talk more about that. All righty, let's see. So this is a schematic of a single acting reciprocating air compressor. And single acting means that it only compresses on one side of the piston. So as you can see in here, I've got a suction valve and a discharge valve. And so when this thing pulls back, it sucks that suction valve open and the air floods into the cylinder. And then when this thing comes forward, it compresses the air. And this is just a much stronger spring. And so it doesn't pop open until the desired pressure. And then you get a pulse of air running out of this thing. And so you do get all of these kind of pressure pulses out of reciprocating. It's common to put a big receiver tank at the exit of a reciprocating. And one reason is to just store air, but the other thing is to dampen out the pulses, the pressure pulses that come from the movement of the piston back and forth. So a big receiver tank can help smooth that out, and so you don't see those pulses so much out in the compressed air system. Okay, so we've got some little characteristics on each one of these. Single acting, reciprocating, you see the inlet and then the outlet valves. So we just compress on one side. You can get one stage or two stage, so you can get a two stage single acting. They're usually air cooled. Most of them are small. If you go to Lowe's, even though these days at Lowe's you can buy a small screw compressor, but a lot of the ones like the automotive shops and all that stuff, you buy them and they got a couple of pistons on them up there, and then they got a big storage tank, and it's like $500 to $1,000 at Lowe's, and you go set them in the shop and turn them on. They just have a pressure band. They pump up to say 110, and then they unload, and then it coasts down to 100, and they just come on and off based on how much air is being taken out of the system. The start-stop control is a very efficient control mechanism. That's actually pretty good. And good point of use compressor to lower main system pressure in large plants. So we also sometimes see a large plant that has one or two small, medium-sized uses that require a much higher pressure than everything else. Maybe you do have a couple processes or a couple pieces of machinery that require 125 PSI. Well, you may be running 10,000 horsepower of compressors. And if this is a small use, you would hate to have all of those compressors pumping up to 125, which would cost you an arm and a leg. So maybe you can set those at 90 and put in a small point of use compressor and take some 90 PSI air and boost it up to 125 or 130 with one of these guys, and just supply that machine with the pressure that it needs. So that's what that point in red is getting to. A rough number on efficiency, and this is how we will rate compressors, is kW, a power required to produce a flow of 100 CFM. That's our specific power, kW per 100. So these guys get a rating of 22 to 24, which is not really great. I mean, it's not awful, not terrible, but not terribly good. Okay, so we noted over here that the start-stop control was actually pretty good. And so we would like to do that on larger compressors, but the problem is only smaller motors can operate, say maybe 25, 30 horse. You get much larger than that, you're going to tear up the motor, because these small compressors like that motor is going to start and stop a lot. If you're using air out of that tank, it's going to start and stop all day long, continually. And it may start every 2 minutes. It may at lunchtime, maybe it goes 10 minutes, but it's starting and stopping all day long. And so what happens is when a motor starts, the inrush current to the motor for that first second and a half, 2 seconds is 6 to 8 times the normal running current. And that puts a lot of stress on all of the electrical components, the wires, the windings, everything that sees that inrush current over and over and over again. It can cause insulation breakdown. It can cause cracks. I mean, it's just, you know, the larger the motor, the less frequently you want to start and stop. Now, that's unless you have a variable frequency drive or a soft starter. Because when those things, if you have that equipment, those things start the motor very slowly. And there's no stress. There's no big stress or strain. So a variable speed compressor with a variable speed drive in it, you can start and stop that all you want. You can have them even time out and completely shut the motor down and bring it back online. You get lots of flexibility. You don't have to worry about damaging the motor and the electrical components. Inrush current typically lasts only several seconds as the motor comes up to full speed. Motor 75 to 100 horse and larger will fail prematurely if frequently started stop. And I'd be concerned at even 40, 50 horsepower really. But anyway, there's some range in there. Now you see the little ones, a 10 horse motor, no problem. 15, probably okay. 20, okay. 25, 30. So there's a transition where they get large enough that this becomes an issue. You can always talk to the motor people about it. There's a picture. That's got 3 cylinders, just to increase the volume of air that it can produce. And a small storage tank, and then you hook in here to take the air out and use it, pneumatic tools or whatever you're doing with it. Okay, double acting reset. These were pretty big boys too. I've seen a few of these at maybe 400 or 500 horsepower, but most of these were 800, 1,000, 1,500 horsepower, 2,000 horsepower. These were pretty big machines. They don't make them anymore. There still are some in operation, but you can't do compressed air, course without talking about double acting recips. So they compress on both sides of the pistons. So say you've got suction valve here, suction valve here. So if it's pulling back to the right, you're sucking air in here and you're compressing over here, and here's your discharge valve. When the pressure gets to the set point, the valve pops open and the air rushes out. So when you get this all the way over to the right, you then have this side of the cylinder charged, ready to go, and then it goes the other direction. And you compress on this side and suck in on the back side. And it just goes back and forth. Okay? So that's what we mean by double acting recip. There's a picture. So we had 4 cylinders on that guy. 2 on this side, 2 on the other side. So it would, so we were producing out of one side, and then we would go to an intercooler to cool. You probably remember from thermo, you can enhance the efficiency of a compressor by doing intercooling, do partial compression, then cool the gas off again, and then finish the compression. So these things all had intercoolers on them. And you had one big motor turning all that. So here's kind of our summary slide on double acting recips. Uses pistons with compression on both sides, usually water cooled with greater than 10 horsepower. I've never seen a small one. 2-stage capacity was very good, our efficiency, 15 to 16 kW per 100. That's a really good number, as you'll see. Our standard number on the screw machines is about 18 or 19. And so this was considerably better than the screw machines. They can go up to pretty high SCFMs. max pressure plus 250. They had lubricant and lubricant-free machines. I've never seen a lubricant-free. The lubricated required a major overhaul, basically every 2 years. And so that's the equivalent of doing a major overhaul on your car engine, where you have to take it apart, change the rings, and all of that. And that's what really killed these things, was that they required quite a bit of maintenance. Efficiency was good. The large companies in the old days had master mechanics and people, and they would just rebuild their own, like, you know, gearheads and guys that would rebuild engines. I'd go to work and they'd rebuild the double acting reciprocating air compressors, no problem. But that skill is pretty much retired, and they can't find people. So you have to go to the compressed air companies, and they charge an arm and a leg to rebuild these things. And so that's done a lot. I saw a bunch of these at Rolls-Royce, and they make helicopter engines in Indianapolis. I spent 2 weeks up there doing energy stuff for them. And this is all they had. And they still had the expertise in the house. They said, oh, we love them. We'll never get rid of these things. They were 30 years old, sitting there purring like a kitten, man. She'd walk up to them, and they're, I loved it. I'm just going to stand there for 5 minutes and just watch them run, you know. Hey, this is a piece of history right here. Another 10, 20 years, you won't see probably any of these things. Expensive, and like I said, they don't make them anymore. But there are quite a number still in operation. Okay, so now we're going to get down to different ways to adjust capacity. So on these double acting recips, you know, let's say this thing can produce 3,000 CFM, but I only need 1,500 CFM. So physically, what's going to happen at the machine is going to reduce the capacity. So we have, looks like at least 1, 2, 3, 4 options. And we'll see that the efficiency of operation at part load changes radically depending on which technology that we use. Part load efficiency is a big deal because air compressors spend their whole life, most of them, or a lot of them, operating at part load. So how efficiently are they when they're producing 60% or 70% or 50% or 40% of their rated flow? So we've got bypass to suction. So basically, on the discharge side, we have this little valve, and we can open this valve, and it lets the air run around. The air that we just compressed, to say 100 pounds per square inch, it lets it run right around and go back in the suction. Doesn't really sound like a very good idea, right? But that's what bypass to suction is. I've got suction throttling. So this is like a throttling valve, and if I don't want any air out of this side, I simply close that valve, and I don't let it draw any air in. So it still moves back and forth, but I just don't let it have access to any air, and that will, if it can't get any air in, it can't get any air out. Okay. This is what's called a clearance. I always want to say clearance, but it's clearance pocket. And it's an extra volume, and it has a control valve. And so if I want to unload the air coming out of this side of this cylinder, I open this valve. And so it pulls the air in, and when it goes to push the piston to compress it, this valve's open, and I've got enough volume that I just push that air up here into this volume, and I really don't compress much of anything because I've got that clearance pocket open. And so these things typically run either open or shut on the clearance pockets. Then we did suction throttling, and then we got suction valve opening. So if I want to unload this side of this piston, I have a mechanism where I can just hold this valve open. And so it just moves back and forth. It pulls air in and pushes it out. and it never builds enough pressure to open the discharge valves. So there's 4 different technologies or different mechanisms by which I can unload this double-acting reciprocating compressor. Well, here's where the rubber meets the road. Okay, so let's take a look at this. So on the vertical axis, percent full load power, okay? Horizontal axis, percent full load flow. So if I'm making full flow, I'm at full power, okay? But the question becomes, if I'm making 75%, 50%, 25%, what happens to my percent full load power? Oh. Well, let's see. Well, bypass to suction, man, I'm going to compress that air no matter what. And then I'm just going to let it pass around here. So guess what? That's as bad as it gets. So if you ever had a compressor operating bypass to suction, you would want to change it immediately. Either that or keep it fully loaded all the time, because it's going to use 100% power no matter how much air you're taking out to the system. That is not a very good deal for the plant. Whoever's paying the power bill is not going to like that. Okay? Then we have suction throttling, which is just trying to restrict the airflow in over here on the inlets, and it unloads along this curve. So I would say at 50% compressed air production, what is that? I'm 87.5% power at 50% flow. Ooh, that's not very good either. It's better than bypass to suction, but it's not very good. It pretty well sucks. No compressed air puns intended. Okay, well, so I've got these others. Several of these have pretty much the same characteristic. And so my clearance pockets operate here. And see that clearance pocket, it's either open or shut. And so on these, I have the ability to run 100%, 75%, 50%, 25, or 0. So if I open all 4 of the clearance pockets, then I produce no air effectively to the system, but I would still pull 20% power. So if that's a 1,000 horsepower motor, you're still paying for 200 horsepower and you're getting no air. So, but as we'll see, in the realm of compressed air, that's considered good. That's considered pretty good. That's how inefficient compressed air is. Okay, what else we got here? We've got these little suction valve unloading. He's got some little diamonds down here. It's about the same curve. Then we've got speed control. And I've never seen one of these on a VFD, but apparently you can put them on there. And that's pretty good. If it's 0 flow, I'm getting down here at 12, 13%. That's a whole lot better than any of these others. And then my best curve is ideal on off. Oh yeah, take my 1,000 horsepower motor and turn it on and off 50 times a day. Oh, it's going to work out really well. In about 2 weeks or a month, you're going to be buying a new 1,000 horsepower motor. Say, boss, I saved $500 on power on the big compressor. He says, yeah, and I'm buying a $40,000 motor because of it. That will not get you your Christmas bonus. I'm sorry. So, okay, so those are the control curves for reciprocating. All right, now this is some log data. We like to put data loggers on air compressors, do it pretty frequently. And let me see, this is You see the amp scale, it's pretty small. That's 140 amps right there, 120, 80, 60, that's 40 amps. So, I mean, this is interesting. This was a smaller, this was 100 horse. This was a Colonial Molding, I think, Colonial something. 100 horse, Chicago was the brand. You don't see many of them anymore, but this was a reciprocating. I think it may have been single acting even, because it was pretty small. You don't see a lot of 100 horsepower like that, but you can see. So it had a pressure band. So if the pressure, so the compressor would operate until it gets to the top of the pressure band, whatever it's at. It could be 110. When the discharge pressure hits 110, the compressor unloads by whatever mechanism it unloads. But the motor doesn't stop, okay? And so so you can see, so it was unloaded because it hit 110. And so it quits producing air, and the users keep using air, so the pressure starts slowly coming down in the system. Let's say it's set to load at 100. So it unloaded back here, the pressure comes down. When it hits 100, the controller says, oops, let's make air. We're at the low point of the pressure band. So the compressor loads 100%. And you can actually see what happens to the piston as the piston moves, the piston strokes on this thing. That's what's so cool about it. You see the piston strokes. And so as soon as you start cramming air back in the system, the pressure starts going up. Yeah.
Can you, like, say you go buy a Ingersoll brand at Tractor Supply, can you adjust when the compressor kicks back on?
Yeah.
So like you can do it at home.
Yeah, you should be able to, I mean, it depends, I guess, which compressor you buy. But in general, yes, those settings are adjusted, for sure. Now, if you buy a small enough one, you know, if you buy cheap enough, you don't need any control. But if you buy a decent size air compressor, yes, you have.
Like you buy with tall,
Well, I mean, you have to talk to them about that. I don't think I can make
I didn't know that. I assumed there was a sensor that controlled that. But I'm curious to know if the entire commercial.
Yeah, I mean, I've got a 15 horse over here, screwed, and I can adjust the discharge pressure and the size of the fan, whether it's a 10-pound van or 15 or a 20-pound van. Yeah, and it's 15 horse. So I would think so, but you know, you would want to inquire. But so my question to you is, why does the current in here, look how the peaks, this thing slopes upward. Why is that? Why does that slope upward? Yeah, the pressure in the system is going up. Let's say it loaded, it was 100. When it unloads, it's going to be, say, 110. And so that's a piston cylinder. It's forcing the same amount of air out with every stroke, right? It's pulling the same volume to the same, out it goes. The motor has to work harder because it has to push into a pipe that's a higher pressure. And so we typically see those things increase, okay? And then, you know, if we had a pressure trace, normally we would have a pressure trace and we would put on here and you would see the pressure at which it loads and unloads and all of that. Well, in fact, there is the pressure trace. Why these things are offset a little bit, they were probably launched on different computers, is what I'm thinking. They normally the peaks line directly up. The higher pressure is logged at the discharge of the compressor, and the lower pressure is out in the system. And you see from peak to peak, that's about a 3 psi drop. well, maybe not even that much, but well, 2.5 down to here. It's probably not even 3. So that's really good as far as pressure drop across the system. But you can see, I think this is for the same compressor, pretty sure. So you can see this one was set to, at the compressor discharge, to unload at 82.5 and to load back at about 73.5. So there was the band that it was running. And you see the pressure is just up and down, up and down, up and down. As soon as it loads, it builds pressure. So we load, we build pressure, we unload, pressure erodes away, just back and forth. And that's what happens to the electrical power on the motor. Okay? So these data loggers will show you in great depth and detail what's going on in the system. Other thing we can do is we can determine how much air that compressor is producing. Because think about it, when it's loaded, it's producing whatever its rated airflow is. Pretty close. So 100 horse is probably 450 or so CFM, 400, 450, between 400 and 500. So for this period from here to here, and you know, do you measure at the top? Do you measure here? I don't know, okay, halfway in between, whatever. It's approximate anyway. But so if you count these little lines, each one is a second on this thing. So you can count them, or there's the software has some tools that will tell you what that is. So this thing was loaded about 36 seconds. So let's just to make the number round, let's say it's producing 500 CFM for 36 seconds. And then it was unloaded for 36 seconds. And it didn't produce anything. So for that, what was that, 72, so for that 72-second period from there to there, what was its rate of air production? Well, it's 500 divided by 2 because it was loaded for 50% of the time. It was unloaded for 50% of the time. Its maximum rate of air production is 500. So it produced, on average, for that cycle, it produced 250 CFM. And so if you get a bunch of this, say over the course of several hours, you can do some averaging. You can say, okay, how much of the time did it spend loaded? How much of the time did it spend unloaded? And you know, it's going to vary from cycle to cycle because you see it did. Say, if you look from here, if you count a cycle from here to here, this one was unloaded for 36 seconds, but loaded for 85 seconds because they're taking for that second period, that second cycle, they're taking more air out of the system, so it has to run longer in order to build up to the pressure that it discharges. So there you go. For the first cycle, it's 36 loaded out of 72, 50%. For the second cycle, it's 85 loaded out of 121, 70%. And of course, that's going to vary throughout the day. But again, if you do some longer term averaging, you can get a pretty good, you can look for the max, you can look for the min, and you can look for the average. Then you kind of get a feel for what that compressor is actually, what kind of service it's being asked to perform in the plant. We've already talked about this. Extra slide. Okay. All right, this is a good time to call it quits for today. We'll jump into rotary screw next time. And so you do need to start reading that compressed air document, the reading material. But the next evaluation is the pump test. I think we said the 19th.
Before you say that you had to pick, would you do a rotary screw?
It depends on the size of the system. And it also depends on the variation in the system. let's hold that question until we get through the discussion of some triggers. And then, because we can have a more informed discussion.
I'm looking at this and looking at I mean, supercharger, that's.
Yeah.
So.
Yeah.
It's got.